So now we come to the twin paradox, which is probably the most famous paradox in the special theory of relativity. In reality, it's a pseudo-paradox, as we've mentioned before, because you can explain it very logically and consistently within the confines of the special theory of relativity, but it just seems counterintuitive to our common sense, and even counterintuitive to some of the principles of relativity, because one of the principles is it seems like things should be relative, right? If you have a symmetrical situation, then what happens to one person should happen to the other if you reverse the analysis. And so let's set it up here. You can see we've got a space-time diagram. We'll get to that in a minute. But so over here we'll have Alice traveling this time. So she's in a spaceship going with velocity v. Bob is observing. And Alice heads over to this star, which is 3 light years from Bob in Bob's frame of reference. Her velocity is going to be 0.6 times the speed of light. And the gamma factor then is 1.25. And just from our previous analysis with things like time dilation, we can see that from Bob's perspective here, let's just start with Bob and figure out, okay, what's going on with Alice? Well, at a velocity of 0.6 c, as she travels away from him, that means if the star is 3 light years away, it will take her 5 years to get there. 5 years times 0.6 times the speed of light gives us the 3 light years, or really other way around, you could say it, that 3 light years times, well, let me say 5 times 0.6 gives us 3. We'll just leave it at that. So what happens here is this is her world line, Alice's world line, going up to 5 years and traveling 3 light years there. And so that's the speed of 0.6 times the speed of light. And then she turns around at that point and comes back again. Okay, so another 5 years. According to Bob's clocks, another 5 years, and then she's back at 10 years in terms of what he is thinking. And then let's think about what he sees Alice's clocks do. Well, Alice's clocks will be time dilated. They will be running slowly as he observes them according to his lattice of clocks. Remember, both Alice and Bob have their imaginary lattice of clocks, all synchronized. And so we know that, we'll just call it, Alice's clocks, T sub A, we'll call it delta T sub A, at a certain period of time in Alice's clocks, is going to be 1 over gamma delta T sub B, because Bob is observing Alice moving. And so if you do the math, which really isn't too difficult here, because if Bob sees 5 years for Alice to get out there, well, 5 years divided by 1.25, so this is going to be 1 over 1.25 times Bob measures 5 years in his frame of reference for Alice to get there, and you get 4 years. So he sees Alice's clocks tick off 4 years. When she gets there, they take a picture. Okay, so his lattice of clocks will read 5 years. Her clock at that point will read 4 years. And then on the return trip, same thing happens, that now she's coming back, but still at a velocity of 0.6 c. Bob will see his clocks tick off 5 years again, because that's how long at 0.6 c it takes to go 3 light years back again. And at the same time, he will see Alice's clocks run more slowly than his, and so he'll see Alice's clock run for 4 years. So we'll have essentially 4 years for Alice here, another 4 years here. Meanwhile, Bob has 5 years and 5 years. So from Bob's perspective, it seems like Alice should come back having aged 8 years, while he has aged 10 years. And you can say that's somewhat paradoxical, but not within the confines of the theory of relativity, the special theory here, because we know about time dilation. Where the paradox comes in, as we'll see in a minute, is Alice's understanding of this. In fact, let's think about that right now, because you could say, well, let's just reverse the situation, because in Alice's frame of reference, she sees Bob moving away from her, right? And we could draw a similar diagram like this for Alice, except Bob would travel over here this way in negative direction and then travel back to meet Alice again, as it were. So whether Bob is on Earth or planet or just his own spaceship there, Alice travels away to the star, comes back again, okay? Or Alice could see Bob from her frame of reference. Bob travels that way, goes that way. The star comes to her, and then back again. The star moves away, and Bob comes this way. And if you do that analysis, from Alice's perspective, she sees her clock ticks off 4 years. And then you could say, okay, so this is Bob's analysis. And then if we do Alice's analysis, she'll say, well, from my perspective, your clocks, Bob, are ticking more slowly than mine. My clock's ticked off 4 years. We both agree on that because that's what my clock read when I got there. But I see your clocks ticking more slowly during my trip out there. If I do comparisons along the way, I see them actually doing 1 over gamma delta TA. And so if you do that, actually, if you do delta TA equals 4, so this is 1 over 1.25, and this is 4, you get 3.2. That's it, something like that. 4 divided, yeah. Okay, 3.2 years. So she sees his clocks tick off 3.2 years there. And so this is where the real paradox comes in. I mean, part of the paradox is just in the idea of time dilation, all that there might be a difference in times when they get back. But the real paradox is Bob can understand just from regular time dilation when Alice comes back that his clocks, her clocks run more slowly. Yet Alice, though, can do the same analysis and say, well, if I observe Bob's clocks going 3.2 years out and 3.2 years back, shouldn't that be 6.4 years total? My clocks run 8 years, while Bob's clocks run 6.4 years. I should expect Bob to be younger when I get back. So what's going on here? You can't have both. Either one is older and one is younger, or they're the same age. And so we have to figure out what's going on with this in terms of the special theory of relativity. Can we explain this so that we can understand that when they get back, Alice actually, the answer is, Alice has aged 8 years and Bob has aged 10 years, and yet this part of the analysis also for Alice is correct. Now, one other thing to mention here, because often when you read about the twin paradox and just sometimes even think about it a little bit, you'll often come to the point that, well, there's a real problem here because for Alice to get to the star, she has to change direction. And to change direction means she has to decelerate to 0 and then accelerate again, or sort of go in a loop. So however she does it, she's accelerating. And as we mentioned before, the special theory of relativity only works for inertial frames of reference when you have constant velocity motion. And so it seemed that just throws the whole thing out the window, that we cannot analyze this situation using the special theory of relativity. And sometimes you'll hear it said that way. The twin paradox, because it involves acceleration, therefore you have to use something like the general theory of relativity, which involves acceleration to really understand it. In actual fact, you don't. The difference in times, as we'll see when they get back, is due to relativistic effects from the special theory of relativity. And here's how we can handle the acceleration. Essentially, we'll make the acceleration, the time of acceleration, deceleration, and acceleration, again, very, very small compared to the travel time. Okay? So in other words, essentially be not quite an instantaneous turnaround there, but decelerate rapidly and then accelerate rapidly and turn around and come back again. And you can make that possible. If it's not possible within our numbers here, you just lengthen the trip that needs to be made. And then you can make the time of acceleration really as small as you want. Now, of course, there are things about, you have to factor in at what level can a human body take a certain amount of deceleration and acceleration. In fact, next week we'll talk a little bit more about that. But we'll just assume for now, yes, we can decelerate and accelerate rapidly enough so that the time of acceleration is negligible compared to the time when it's at constant, when Alice is at constant velocity there. But as we'll see, the key point about that deceleration and acceleration, and actually as you can see from the diagram here as well, is that Alice changes her frame of reference. And that's what we have to take into account. And as long as we take that into account, then we can analyze this from the perspective of the special theory of relativity and understand that, yes, Alice will see Bob's clocks when she's traveling along here on the outbound trip. She will observe Bob's clocks ticking away and a total time of 3.2 years, while hers do 4 years. Meanwhile, Bob sees his clocks 5 years and hers at 4 years on the inbound trip as well. She'll see Bob's clock's 3.2 years, while hers do 4 years, and Bob will observe his clocks for 5 years. So that's what we want to understand. And what we're going to do in part 2 here of the twin paradox is break this diagram down, expand it out to the outbound trip and the inbound trip, and do two combined space-time diagrams, actually, to see if we can understand a little bit more diagrammatically, visually, what's going on with the twin paradox.